Hi, this is Professor Merrill-Lichty. In this video, we're going to continue our discussion of simple regression and correlation by emphasizing inferences that can be made using these tools. Let's look again at the steamboat example, where Y is the amount spent per day at a ski resort in dollars, and X is the income in thousands of dollars. And here's a partial printout from Minitab. When we're doing linear regression, the primary question we want to answer is whether there is a relationship between the two variables, x and y. And we can do this using a hypothesis test. So nothing different here other than the details are a little different. The null hypothesis says there is no relationship. Think of that as saying the simplest explanation is the best explanation versus the alternative hypothesis, which says there is a relationship. And that's signified by saying that beta 1 is either equal to 0 or not equal to 0. So if you think about this, our model says y is equal to beta 0 plus beta 1 times x plus the error term. And if the null hypothesis is true, what does that mean about the x? It's going to be multiplied by 0, and so that's just going to drop out. And we're going to have the intercept, beta 0, plus a random error term. So how do we perform this hypothesis test? It's just like all the other ones that we have. First of all, we write down the null hypothesis and the alternative hypothesis, and then we look at the test statistic. In this case, we have a coefficients table that's given to us as part of the regression output, and the coefficient for income is 3.64, and we can use that to come up with a test statistic of 11.22. Now we're going to do this hypothesis test at the 5% level of significance, and let's look at the steps. Our test statistic is going to be a t, random variable, and it's 11.22. Notice that's given to us right here in the output. The degrees of freedom for simple regression are going to be n minus 2. In this case we have 10 observations, so there's 8 degrees of freedom. And our decision rule then is going to be based on a t-distribution with 8 degrees of freedom, and this is a two-tailed test, so we have the rejection rule that says if our test statistic is bigger than 2.306 or less than negative 2.306, we're going to reject the null hypothesis. So in this particular example, our test statistic is 11.22, and that's bigger than 2.306. Also, we're given the p-value for free up here, and we compare that to 5%, and we see that's much less than 5%. So both of those tell us that we should reject the null hypothesis and conclude that there is a linear relationship between income and the amount spent per day at Steamboat. I highly recommend that you use software in order to come up with these calculations, but I want to show you manually as well how to do this. So if this is my data, I can calculate y hat, the fitted value, and that will lead me to the residual. And if I square the residuals, then I can sum all these things up. And I will also refer you back to the last video where we came up with some of the other calculations needed here. The calculations we need are the sum of squares for the x's, which measures the total variation in the x's, the estimate for the standard error, and again, we talked about that in the last video. So we have 13.0336, and then we need to use those things to come up with the standard error for the coefficient b1, and to get that we just take s of yx divided by the square root of ssx. And finally, the test statistic that we're calculating is b1 minus 0. Note that 0 is the value that we hypothesized in the null hypothesis. And so we're taking the point estimate minus the hypothesized value, dividing that by the standard deviation of the point estimate, and so we divide by S of B1. And this gives us our test statistic, which is a t random variable. The second inference we can do addresses the question of how accurate our estimate is. And if we look here at the regression output that we have, we see that we have a point estimate for the slope to be 3.64, and we're also told this the standard error, the 0.324, and of course we divide this by this one, we got our t value, but we want to come up with a 95% confidence interval. And since we're dealing with a t distribution on n minus 2 degrees of freedom, we can write down the formula b1 plus or minus the t value with alpha over 2% of the area to the right of it times the standard error of b1. So we can just plug these numbers in. We've got 3.64 plus or minus 2.306. That's what we had for our critical value when we did the hypothesis test on the previous slide. And then we multiply that by the standard error of the coefficient 0.32. And that gives us a range from 2.89 on the low end to 4.39 on the high end. This means that we're 95% confident that the population slope beta 1 is somewhere in that range, somewhere between 2.89 and 4.39. Now you might say that's a big range, and you would be right in saying that. Why do we have such a big range? Well, probably because we've got only 10 data points, and so there's not a lot of information contained in those 10 data points. The next inference we're going to talk about is based on the analysis of variance results that are given to us with our regression output. In order for us to be able to understand this better, we need to try and figure out the source of the variation in the y variable. And if you think about what we're saying with our model, we have y is equal to beta 0 plus beta 1 times x plus an error term. And there's really two components here that vary, the x and the epsilon. So x is our independent variable. In this case, we're talking about income. And if you think about people that go skiing, the income of these people is going to be a random variable. It's going to be different for everybody. And so one source of the variation we have, if there is a relationship between x and y, is the x. And that makes sense, and that's really the part that we're trying to explain when we do regression analysis. The other part is stuff that we can't explain with our model, and sometimes that's going to have other factors that maybe we could put in the model, but there's always going to be some error or randomness as part of that. So the two sources are the x variable and randomness. So we can test whether there's a relationship between x and y using an F statistic, which comes from our analysis of variance, and it gives us the same result as if we do the t-test. And the idea here is if there's a large amount of variation due to the x in comparison to the randomness, then that suggests that there is a relationship. So the degrees of freedom for the F random variable are going to be 1 in the numerator and n minus 2 in the denominator. The analysis of variance table comes as part of the regression output. It allows us to test the same exact hypothesis that we did previously with the t-test, and that is that beta 1 is equal to 0 versus the beta 1 is not equal to 0. The test statistic here is going to be an F random variable, and in this case it's 125.87. It's given to us right here. It comes from taking this number, 21,383 divided by 169.9, and it has 1 and 8 degrees of freedom in this case. So our rejection region is going to be the top 5% of the F distribution, and that's going to be anything bigger than 5.32. So what's our result for this example? We have an F statistic of 125.87. That's bigger than 5.32. So we're going to reject, and it's very strong. We can see the p-value is 0 to 3 decimal places. And again, that's the same result that we got when we did the t-test. Let's look at the similarities between the F and the t-test in a little more detail. Remember, our test statistic for the t was 11.22 with a critical value of plus or minus 2.306. With the F statistic, we had 125.87 with a critical value of 5.32. And it turns out if you square the t statistic, you get the F statistic. And there might be some rounding error there, but if you take it out to enough decimal places, it's going to be exactly the same thing. And that's because an F random variable on 1 and n minus 1 minus 2 degrees of freedom is just the square of a t on n minus 2 degrees of freedom. If you square the critical value, 2.306, you get 5.32, which is the critical value for the F, which simply means that we're always going to get exactly the same conclusion when we do the T or the F tests for simple regression. So what other inferences can we do with regression? Well, we've already done a point estimate for a prediction. Remember in the last video we said, what if somebody makes $44,000? What's the point estimate? Well, we can do that, as we've already done, but we can also come up with a 95% confidence interval for that same estimate. So you'll recall that we plugged 44 into our equation, and we got a point estimate for somebody who earns $44,000, that they're going to spend $169.79 per day at Steamboat. We just calculated a point estimate for the average response variable when x is equal to 44,000. What we want to do now is calculate a confidence interval. In other words, we want to know how much variability is there in that estimate. And again, keep in mind we're doing this for the mean, for the average response. So for all of the people that have an income of 44,000, we want a confidence interval for the average daily expenditures at Vail Resorts. And there's a formula for this. It's kind of a mess, but it starts with the point estimator that we just came up with, and then we're going to add and subtract, just like the other confidence intervals we've done, t times the standard deviation of the point estimator. So let's look at the numbers that we have here. 169.79, that's the point estimator, plus or minus 2.306, that's the critical value that we came up with. 13.0336, that's the standard error for the regression, times the square root of 1 over n, we have 10 observations, plus here we have the predicted value of 44 minus the average value for the x's. So square that, divide by the sum of squares for the x's, and we get an interval from 157.55 on the low end up to 182.03. And so we would interpret that in the same way we do every other confidence interval. Say we're 95% confident that the daily spending amount for people that make $44,000 a year on average at Steamboat is between $157.55 and $182.03. Okay, here's the last inference that we're going to do in this video. What if instead of talking about all the people that make $44,000 a year, we want to talk about just a single individual, and we're going to call this person Kim. So we know that Kim makes $44K a year, and we want to come up with a prediction how much they're going to spend per day when they visit Steamboat. So if we plug our 44 into the formula that we have, we get 169.79, so about $170. And that is the point estimator, but it doesn't tell us anything about how accurate the point estimator is. So we're going to use a prediction interval, and it looks just like what we did with the confidence interval for the mean, but the difference is here we're talking about an interval for a single individual, and the formula is basically the same except it has this 1 added in here inside the radical. So if we plug all of our numbers in, we get 137 on the low end, 202 on the high end, and we can say we're 95% confident that Kim will spend between $137 and $202 per day when she visits Steamboat. You maybe noticed that the prediction interval for Kim was much wider than the confidence interval for the mean response. And why is that? Mathematically, it's easy to see. There's an extra 1 inside the radical, and that makes the interval bigger. But intuitively, what's going on here? Well, it's going to be more difficult to pin down a single future response than it is a group average. And why is that? We came up with a confidence interval by estimating the average for all people with an income of $44,000. And that's a good place to start if we're going to try and estimate Kim's income. But we can't really expect Kim to spend exactly at the average. In fact, there's going to be inherent variability for each individual, and that's really what we're taking into account when we calculate the prediction interval, and that's why the prediction interval is always going to be bigger than the confidence interval. So all of these calculations done the hard way are hard, and if you use Minitab or other software, it turns out not to be too difficult. So in Minitab, you're going to go to Stat, Regression, Regression, and then Predict, and you'll see this prediction window open up. Now, you should see the response already populated, and you just have to go then and put in the income value or values that you want to use for calculations. The only other thing we're going to worry about here is options. We'll look at that in just a minute. But let me say before we do that, you have to have run the regression model before you can do this. And that's why the response variable is going to be pre-populated. And if you don't run the model before that, then Minitab's not going to know what regression line to use. Under the options, you'll notice a confidence level field. You can change that if you like. The default is 95%. That corresponds to an alpha level of 5%, of course. And for this course, we're always going to use a two-sided interval. So click OK a couple of times, and you're going to get this output here. Notice the first thing it says is the regression equation, y is $ spent is equal to 9.6 plus 3.64 times income, and the x value that we're using to predict is given here. If you put in more than one prediction value, then you would see more than one line here. And what do we get out? First of all, we get the point estimator, or the predictor, the point predictor, and in this case 169.789. And then we get a confidence interval for the mean response, and notice this is the same one that we calculated a few slides ago, and it goes from 157 up to 182. And then finally we get a prediction interval for an individual like Kim, and again this is the same as what we calculated before when we plugged the numbers in. So using Minitab is much easier and quicker and just as reliable as, or probably more reliable than plugging the numbers in yourself. And so that's all I've got for this video.